Hello everyone. So this video is going to be on continuity of functions. So we'll first review continuity at a point and then look at continuity on an interval. So what are continuous functions? So put in a very simple intuitive way, continuous functions are those which have the property that you can draw these functions without ever lifting your pencil from the page. And that's another way of saying that when you draw a graph of these functions, there's going to be no break in the function. So a break in a function would mean that the function is going to be discontinuous at that particular point. Now, I've given you a very brief intuitive definition. Now let's try and define it in a formal way. Okay, so we say that a function is continuous at a point if you can draw a graph of that function at that point. So we're now talking about continuity at a particular point, say C, where C can be any constant. And we're first interested in understanding the notion of continuity at that particular point. So if you're able to draw a graph of that function at that point without ever lifting your pencil from the paper, then the function is continuous at that point. Or in other words, it's continuous if there is no break in the graph at that point. Now, in this case, let's look at the case of C, where C is any constant, or x is equal to C, or any particular value. If you look at the function in green, f of x, and when I draw this function, as I cross C, there is no break in when I drew it. So I just drew it in a very smooth fashion. There's no break at C. So f of x is continuous at C. Whereas on the other hand, if I'm looking at the purple function here, g of x, and I start here and I draw the graph there, but boom, when I come to C, the function, there's going to be a break here, or rather a jump. So I start and come this way, and I now jump, lift my pencil from the paper, and start drawing the function again that way. So g of x has a break at C, and therefore it is discontinuous at C. Now, let's define all of this in a very formal way. What are the conditions that we need to have in place for a function to be continuous at a point C? All right, now let's build the conditions one step at a time. We have this function f of x, which is given to us, and we're interested in evaluating continuity around the point A. Now, the graph of the function looks like this, and when there is A, the function is undefined at A. So I lift my pen, and then I start drawing it again from that point. So I start here, but when A comes, the function is undefined. So I lift my pen, and then start drawing it again. So we see that there is a break because the function was undefined at A. So one of the conditions that we require to have for a continuous function is that for a particular input value, the function is defined at that value. Or in other words, for an input A, f of A should be defined. And that's one of the first conditions we need to have in place for continuity. Let's look at another case. We have this function in purple here. And how does this function look? So we start drawing the function from that point, and we slowly get to A. And because it's a solid circle at A there, the function is defined at A. But to draw the function beyond A, we're going to now have to jump from here to there and then start drawing f of x again. So we start here and we come up to A, and for values of x greater than A, we jump and we start doing this here. So you see how I had to lift my pen from the paper and move here? There was a break at A. And earlier, in the first case, we saw that one minimum condition for continuity is that the functional value is defined at A. Now, in this example, you see that the functional value is defined, but still we have to jump. And why did the jump come about? That jump came about because the limit of the function as x tends to A does not exist. Because if I approach A from the left-hand side, the limit is given by this solid value. If I approach A from the right-hand side, the limit is given by this hollow circle. So, and these two numbers are not the same. The left-hand and the right-hand limits are not the same. Therefore, a two-sided limit or a limit does not exist in this case. So another condition for continuity is that a limit to the function exists at that point A. Now let's build on this even further. Let's look at this orange colored function here. So we draw it like this, but when we come to A, the function has a hollow value here, but rather at A, the function just takes on a single value. And then for values of x greater than A, we jump back to this function and draw f of x this way. So you see how there were two jumps that I did here? I mean, my pen had to lift from the paper twice. So I draw it this way, but to plot the value of f at A, I jump here. And then for values of x greater than A, I jump back and I draw the line. So the first condition, is the function defined at A? Yes, very much, it's defined. Does the limit to the function exist? It does, because if I approach A from this side, my function approaches this hollow value. If I approach A from this side, my function again approaches this hollow value. So the limit again exists, but I still had to jump. I couldn't draw this function in a single straight line. So that brings us the third condition, that a limit needs to exist and a functional value needs to exist at A, and these two have to be equal to each other. That is, the limit of f of x as x tends to A should be equal to the functional value at A. And that's the penalty, that's the final condition. And if you recall in the lecture, I had told you that the function is continuous if this condition holds. But now you see how this, when I just stated this condition, just by itself, I was implicitly assuming that f of A exists and limit of f of x, the limiting value also exists. So, but right now in this video, I'm kind of laying it out in a much more clearer way for you. So the final and the most important condition for continuity is that the limit exists and is equal to the functional value at that point. And when I say the limit exists, I mean that the limit has to be, both the left-hand side limit and the right-hand side limit have to be the same. And that's when I say the limit exists. Let's see a summary of all the conditions that I stated. F of A should be defined, the limit should exist, and the limit should equal the functional value. If any of these conditions don't hold, then the function is discontinuous at point A. Now, how do you go about determining continuity? Step 1, check to see if the functional value is defined. If it is not defined, you know right there that the function is a discontinuity at A. If the functional value is defined, then you go to step 2. Check if the limit exists at that point. If the limit doesn't exist, you already know that there is a discontinuity. If the limit exists, then you go to step 3. Check if the limit is equal to the functional value. If it is not, then the function is discontinuous. If it is, then if it is continuous, at x is equal to A. Now, just a few examples to check our understanding of these cases. Now, this is the given function. Check if it is continuous at x is equal to 2. Step 1, find the functional value at x is equal to 2. And we get 4 by 4 minus 2 minus 2, which is 0 by 0, undefined. Therefore, we know that it is discontinuous at x is equal to 2. Let's look at the second example. Oops. Right. So we have this piecewise function, which is defined to be x squared plus 4 for all values of x less than or equal to minus 3, which is what I've drawn in this parabola here. And it's defined at x is equal to 3. For values of x less than or equal to 3. Now for values of x greater than 3, it's going to be 4x minus 8. Is this function continuous at x is equal to 3? Let's do the steps. So is f of 3 defined? Yes, f of 3 is given by minus 3 squared plus 4. So it is defined. Now, does the limit of f of x as x tends to 3 exist? Well, what's the left-hand side limit? As x tends to 3 from the left-hand side, which is where we're moving in this direction, the limit happens to be, I think it's just going to be If I approach 3 from that side, it's going to be minus 9 plus 4. So the limit here is going to be minus 5. As I approach 3 from the right-hand side, what's going to be the limit? Well, if I'm approaching 3 from the right-hand side, I'm going to be looking at the functional value right there. And that seems to be approaching, I believe, 4. And you see how the limit doesn't exist here, where the left and right hand limits are referring to two different numbers. So the limit doesn't exist here. So I'm sorry, it is discontinuous at 3. And I'm going to leave the third one as an exercise for you to check if it is continuous at x is equal to 1. Check for the functional value at 1. Check if the limit exists at x is equal to 1. And check if the limit is equal to the functional value at that point. So that is going to be an exercise for you. Another point to note is that polynomials or functions of x polynomials are ones where a linear function is a polynomial, quadratic function is a polynomial, a cubic function is a polynomial. By default, these polynomial functions are continuous at every point that is in their domains. So that's just a really easy way to compute or understand both continuous functions as well as the idea of limits. So for what values of x is this f of x equal to this continuous? So this is a polynomial function where x has been raised to the power 4. So if this continues, by definition, it is continuous for all x belonging to the set of real numbers. Remember, they're continuous at every point in their domains. And this particular function can take on the domain of x, of any x belonging to the real number line. So it is continuous for all x belonging to the set of real numbers. For what values of x is this function continuous? Well, it's going to be continuous at every point in its domain. And in its domain, it's going to include all x except x is equal to 5, because at x is equal to 5, the function is undefined. Therefore, continuous at all x belonging to the real numbers except x is equal to 5. Another example. Polynomials are by default continuous at every point in their domain. And this also applies to ratios of polynomials. So here I have a cubic function, and in the denominator I have a quadratic function. And by default, they are continuous wherever they are defined or at every point in their domain. So we don't have to worry much about the numerator because it's defined at all values of x. Whereas we have to worry about the value of the denominator. Now the denominator is going to take on values of 0 when x is either 2 or minus 1. So in essence, y is going to be therefore continuous at all x except when x is 2 or x is minus 1. All right? And therefore, we know that the function is going to be continuous at all points except when x is 2 or minus 1. So when I ask you to find the limit at x is equal to x tending to 1, then the function is continuous at x when the value of x becomes 1. So in order to compute the limit of this expression, all you have to do is plug in the value of 1 into this fraction and compute the limit. So to repeat, the ratios of polynomials are going to be continuous wherever they are defined. And we see that y is going to be defined for all x except when x is equal to 2 or minus 1, because at those two values, the denominator will become 0. Therefore, y is undefined. So once you know the domain for this function, it's going to be continuous at all points in the domain. Now, if it's going to be continuous at those points, and when I ask you to find the limit as x tends to 1, this y is going to be defined at x is equal to 1. So it's going to be continuous at x is equal to 1. And if it's going to be continuous, the limit at that point is nothing but the functional value of the function at x is equal to 1. So I find this by substituting x is equal to 1, and you will get the answer to be x tends to 1, 4x cubed plus 5 by x squared minus x minus 2 is just going to be 4 plus 5 by 1 minus 1 minus 2, it's just going to be minus 9 by 2. So I will stop this video here, and next one will go over continuity over an interval. I will see you there.